UDP, all it provides really is multiplexing. So you can have many servers which are using UDP, but by the port numbers, we can distinguish the messages coming to them. Checksum is optional, and obviously there is no retransmission, there is no sequence number, and no flow control, and so on and so forth. So, but there are applications that can live with this kind of thing, and those are network management, DNS, multimedia, and so on and so forth. And so these are the only fields in the UDP header. You have a source port, destination port, length, and checksum. TCP. TCP stands for Transmission Control Protocol, and it provides only 3 services: send, push, urgent. Send simply means that please send whenever you can. I am not in a hurry. And by the way, those of you with the laptop, either you close the laptop or you make sure that you have a justification for why it is open. Because I have given you the handout, so you should be looking at the handout and not at the laptop. Please close it. Alright. So, send means please send when convenient. And please close when convenient. So, I am still looking at, because that is kind of coming in the way. So the idea is that you might say, give it to TCP, but it may not send it. And then you give it the second byte, a second packet, it will not send it. And then it will try to optimize, minimize the number of messages. Okay? Second is push. Push means, I want to send it now. Yeah. Okay. The question is, does each router get to choose when to send? No, routers don't even look at TCP. Let's go back again. There was one slide in the beginning where we said that this is a layer 4 protocol and routers look only at layer 3 protocol. So the TCP is looked only at the source and the destination. So the routers just handle the packets as they come. They don't look at TCP header. It may not even be a TCP packet, they don't know TCP from UDP. Okay? But the sender knows that this is TCP and UDP, and they are looking at the header. The TCP module only exists in the sender and the receiver. It doesn't even exist in the router. Does it make sense so far? So I show you this slide. Fine with that? Right. So it's only applied at the sender end. At the sender end, if you say push, it will send it all now, which means that if I have given you 1 packet, 2 packet, 3 packet, whatever I have given you, please send it now. Push. Urgent. Urgent means this is an instruction not for the source, for the destination. When the destination gets that urgent packet, then it says that please give it to the user. And so this is like a push at the receiving end. Okay? Because at the receiving end, the TCP may collect and not give it to the user. Alright? So this one says give it to them. And it is not given out of order though, in the sense that if you put an urgent on packet number 5, 1, 2, 3, 4 will be given and 5 will be given at the same time. Okay? Now the push has no effect on delivery, and the urgent request the quick delivery on the receiving end. So there are 2, one at the receiving end urgency and one at the sending end. At the sending end we look at the push, at the receiving end we look at the urgent bit. These are actually 2 bits, push bit and the urgent bit. Okay, so this is clear as to why we have 3 things. We have send, we have push, and we have an urgent. Urgent is generally used for control C. What is control C? When you want to abort. Right? You are doing something and you want to cancel it, you put a control C. we want to tell the receiving end that, look, I am given up on this right away, so they can do whatever they need to do next. Right? So that is urgent. Push is used on character return and line feed. You are typing A, B, C, D, E, F, G, H. TCP is not sending any of it. Right? But when you press character return and line feed, then your program that is collecting all this may say to TCP, please now send this line, maybe some answer will come back. Alright? And the reason that they don't send on every byte is because there will be just too many messages, so they keep collecting as much as they can. Yeah. Not priority, it will just push all of them. So they always will be, the queue of packets which are waiting there will, along with that, the control C will be given to the receiving end. So that's why it says carefully. Urgent data is delivered in sequence. So it is not that you get a priority and you get over the sequence. So if packet 1, 2, 3 are waiting and 4 is urgent, 1, 2, 3 and 4 are given. Oh, if you send 4, it will not be given. 1, 2, 3, 4 will get into the queue and wait there. The difference is that the whichever has urgent will not wait, but it will push everybody ahead of it also. Push everybody ahead. Means that will be delivered to the user, delivered to the application process. Yeah, delay. It's just the delay. Okay, let me try one more time. If you don't put urgency, what will happen to packet number 4? Tell me, what will happen to packet number 4? Packet 1, 2, 3 are waiting at the destination. What will happen to packet number 4? You need to just get into the queue and wait there. Yeah, so that's a good question. Basically, so the idea is the packets, when they come in, they would be generally waiting for some reading process to read. And so I think what will happen is the operating system will probably wake up that process and say, come on, take it right now. So there is something done at the operating system level to wake up that process and so that it can be given to that process. Maybe, yeah. Maybe. So basically, so the idea is before we could not, with normal process, we will go through normal sequence, round robin or whatever we are using, and so that's why the packets are waiting in the queue. But with this control C, we will somehow bring up this process, make it live, and give it. Good question. All right. So we understand the 3 different kinds of send. Then we also have to remember one thing which I actually should emphasize at this point, or maybe later on, maybe this point is a good point, is that TCP is a streaming protocol. A stream protocol. It's not a packet-oriented protocol. It means that if you give it packet number 1 with 2 bytes, packet number 2 with 5 bytes, it may just make one packet of 7 bytes. Or it may make 2 packets, one of 6 bytes and another one of 1 byte. So it doesn't maintain the application packet boundaries. It just treats them like a stream. So suppose you put something in a river, you put 2 packets, one of 5 bytes and one of 6 bytes. A second later, can you figure out where the packets are? They're all mixed up in the water. Right? Similarly, TCP is a stream protocol. It takes byte by byte and delivers byte by byte, not at the same boundary that you gave it to. Yeah. You might have given it 15, for example, 15 characters at one after another, 1 character each. It might give all 15 at the same time to the destination. So the boundaries are not maintained. It's a stream protocol. So basically, you are putting the packets in the stream and they're just being taken off at appropriate time whenever convenient. Yeah, so that's why you need this push and urgent. Is because whatever the application gives, the TCP just keeps into a buffer. And you might give more, and it will keep into the buffer, and then it will send it whenever it thinks it's the right time to send it. But at that point, it may make a right size packet and send it, so it may not send everything. Yeah. Same thing, it just gives 3 bytes as they come in. It generally gives, as the process wakes up, we give it to the process. But the important thing to notice is that the boundaries are not maintained, the packet boundaries are not maintained. It's just that you will get every byte in the order it was sent. Given here, it will come out exactly in the same order there. So it's basically a byte-oriented protocol. Byte-oriented protocol, you give it 17 bytes with 1, 2, 3, 4, 5, 16, up to 17. It will give exactly the same order, 1, 2, 3, 4, 5, up to 17. There is no boundary. Yeah. Variable size, most applications are variable size packets, but if you want that now is the end, for example, you want to do HTTP and you start the HTTP message, you have a get and you have the URL and you have all these fields and then you have a blank line return something. At that point, really you want to send the message, because if you didn't send the message, I mean, you won't get a response. So you will put a push. After the first line, this says get, you are not going to put a push. You will say get URL, blah, blah, blah. If modified since, you can also, but at the end, when you really want a response, you say push. Then the message will be sent. Is that clear now? The streaming part? If it's not clear, ask again. Basically, it sends money when you say push, or it can send it also. The thing is, remember the days it was designed, that time the main application was telnet. And telnet means, remote desktop or something like that. And people were typing, and if every character was sent, there would be too many messages. So they said, what TCP will do is, it will wait for 200 milliseconds. If the second character comes in, maybe it will not send, and then it will send after it does nothing, it type for 200 milliseconds, or 200 milliseconds are passed anyway. So there will be one packet per 200 milliseconds. Yeah. Is a byte, huh? Is a byte. Yeah, that's the thing I want to say. That's the thing, it's all packet-oriented protocol, but the TCP deals in bytes. And it's sent by, so this will become more clear as you go into this one, because everything, acknowledgement and everything is in bytes, not in packets. So when you say at 13, it means that I received 13, I am expecting 13th byte. Okay? So maybe that is another way to think about it, that the TCP is a byte-oriented protocol in terms of payload. So the header. The header has a source port, 16 bits. Destination port 16 bits, sequence number 32 bits, ACK number 32 bits, data offsets 4 bits, reserved 6 bits, then 1 bit of U, A, P, R, S, F, then 16 bits of Windows, 16 bits of checksum, 16 bits of urgent, and some option fields, some length, and padding of some length, and then the data. So all of these numbers are the bit lengths of the fields. Yeah. What is what? Yeah, so I'm going to come to those numbers. Actually, I'm going to go through each of the fields one by one, and we'll talk about what is UA, PRS, what is sequence number, and all that. But right now, this is the whole picture, and that's why I go into the field by field. The whole picture of the TCP packet. Actually, that's another thing. TCP's packets are called TCP segments. So a TCP segment has this header all the way up to here, and then followed by data. Okay? So in the TCP IP world, every layer had a name for its unit, and that name for the TCP is segment. Another way to represent the same thing is in a two-dimensional fashion. Sometimes they present it in, I like it in one dimension like this. So every field is clear. But some books do use it in two dimension, and your book probably uses the same format. Is source port 16 bits, destination port 16 bits, sequence number 32, ACK number 32. Now the only thing we have is not clear is how many is data offset, how many is reserved, and how many are these. So we really need to know that this is 4-bit, this was 6 bits, and so on and so forth. Window is 16-bit, checksum is 16-bit, Urgent is 16-bit, options as many as you want as the padding. Why we need the padding? So to be clear, we need the padding so that everything becomes the multiple of 32 bits. If suppose your options add up to 16-bit here, then you need the padding of 16 bits. Yeah.
So say you have a message of 10, 24 bytes, how would it split that up into data? And is it ever more efficient to split into smaller segments rather than larger segments?
Okay, so let's see, your data is 1024 byte. This is the data. Okay, so we will add this much header, which you can see is 1, 2, 3, 4, 5. Maybe there is no options and no padding. So let's say you have 5 32-bit words here. 5 times 4, 20 bytes header. So we'll take your 1024 byte plus put 20 byte header and give it to IP. The question is whether you will take 1024. What if it was 1000 instead of 1024? It was 10,024. So, yeah, right. So there is something called, later on coming up, is maximum transmission unit. And some routers cannot handle more than 512 bytes. So there is that transmission unit, and then we will just break into that kind of sizes. Yeah, here it actually is called MSS, maximum segment size. So when you install your TCP, you can tell it that the maximum segment size is such and such, and it will use that as the maximum segment size. Yeah. I'm sorry? If you don't? Oh, no, it doesn't send by byte. Okay, so let me say. What I meant was it really does all its accounting and transmission in bytes rather than, basically bytes in the sense that, so when we see this sequence number, ACK number, it will become more clear that what I mean by bytes. It doesn't really say that I'm sending you 2 packets or 2 segments. It says I'm sending you 13 bytes. So all the accounting in TCP is in bytes, not in packets, not in words. So let me just come to that point in a minute. Source port. Source port is 16-bit and destination port is 16-bit. Generally a standard number is used. So 21 for FTP, 23 for Telnet, 53 for DNS, H3 for STTP, and so on and so forth. Destination. Sequence number is 32-bit. Sequence number of the first byte in the segment. So this tells you the sequence number of the first byte in the segment. So this is the first byte here. So if the sequence number is, let's say 0, that means that is the 0th byte. If the sequence number is 100, here this number is 100, then this is the 100th byte. Okay? If the sequence number is 500, then this is 500th byte. Now, there is a field here called SYN, this field S. If that bit is set, that means we are starting, synchronizing. SYN, SYN, stands for synchronizing, means starting. So when you start a new TCP connection, your first message is a SYN message. I want to set up a connection. You will set that bit, S bit there in that packet, and whatever number you put that number is your starting number. So the first byte is not always 0. First byte could be 2031. Yeah.
Why would you set it to something other than?
Okay, so I'm coming to that in a minute. So first byte could be any number, and that number is specified here. Sequence number 2031. So my first byte is 2031, but the SIM bit is set. So you don't have to be concerned. We are starting our counting from 2031. If the SIM bit is not set, and you suddenly get 2001, 31, and you didn't get anything before, you get concerned. What happened to the bits from this before? Right? But the SIM bit is set means this is the first message of the whole connection. So we are synchronizing. So synchronize sequence number. Now, why would you have a different number here? So that some old packets do not show up again as a new packet. So suppose I have already talked to you and I sent you 2000 bytes. Now we close the TCP connection. Now we set up a new connection. Now we start from 0 again. There might be some packets of the old packet which have 0 byte. They might be floating still in the internet. They might show up. We don't want to confuse them with the new connection. So the new connection will start from something higher than where we left off last time. Does that answer your question? Okay. So we don't always start from 0. We start with a number which is higher than where we left off last time. Okay, is there anything going on the computer that is important? Yeah. All right. So basically, so the idea is, so let me see, where are we right now? All right, we are in destination port sequence number. Okay. The next thing is ACK number. ACK number says next byte expected. So when you see ACK 2000, that means I have received 1999. Byte number 1999. I am expecting 2000. I haven't received 2000. Add 2000 means I am expecting 2000. I have received 1999. Yeah, everything before that I have received. When I say add 2000, I have received everything before 2000. I am waiting for 2000. Data offset. This is 4 bits. It is the 32-bit words in the header. So this header, as shown here, if we didn't have options and the padding was 20 bytes long, if you want to calculate in 32-bit words, it is only 5 words. And therefore, the data offset would be 5 words. 5, number 5. Yeah. Yeah, so it's saying that I'm expecting 2000. Oh, so what is happening is both sides are sending to each other, right? So this side which is sending this packet says, here is my packet. This starts from from byte number 200. From you, I have received everything up to 1999, and from you I'm expecting 2000. So this is the source could be sending. So there is no source and destination as such. Basically, A and B are talking. So A sent a packet to say that this is my sequence number and this is my ACK number. Oh yeah, when this packet was sent, at that time this ACK was generated, right? So the thing is A and B. A sends, let's say, 10 bytes from 1 through 10. It's a small request. B sends a big message from, let's say, B is counting from 1000, and it sends 1000 to 5000. That's too large. expecting 1501. Does that make sense? Okay. Data offset is simply the header length in 32-bit words, and this is another complication in TCP IP, is that every layer has its own unit. TCP decided to have the unit of 32-bit words. IP has a different unit. Applications have their own units, so everything counts in different units. TCP counts, at least the data offset, they count in 32-bit words. Reserved 6 bits. Now, somebody asks what is reserved? Every protocol has some reserved bits, because in future, if you want to allocate some bits, so right now we just leave them unused. Later on, we can give some names to them and use it for something. And so later on, when the applications look at those bits, if they don't understand what this bit is, because it was reserved before, their old system, they will be told that if you see a reserved bit, either ignore it or throw away the whole packet. So there is a rule for each protocol as to what to do with the reserved bit that you don't understand. And so reserved bits are right now reserved, 6 bits, which should be generally the 0, but we could just make a rule that ignore. It doesn't matter what they are, you just don't worry about it. That is a okay question from here first.
Have you ever said something that would have more packets than 2 in 32nd and 3 packet number?
Right. So the question is, what happens when you go sequence number wraps around? The answer is yes. Sequence numbers do wrap around. So just like we had shown in the previous example, 0 through 7, here it is 0 through 2 raised to 32 minus 1, and back to 0. Hopefully it will know. Hopefully it will know, because it will know that I'm expecting 2 raised to 32 minus 5, and I have gotten 2 raised, 20 from this. So it's just system. Okay, sequence number is the sequence number of the byte. Remember this example here. This is just one packet here, but the bytes are from 1000 to 1500. You get the sequence number that this is 11 is the sequence number of the first part. Right. Yeah. So each time you send the packet number, the packet is not a packet number, it's the byte number. So it will be, the sequence number will go up by the number of bytes in the previous packet. Okay. That is why now it's become clear as to what is the streaming business is, right? The streaming protocol is that it is not a packet-oriented protocol, it's a byte-oriented protocol. Alright, 6 bits, U, A, P, R, S, and F. The real names are urgent, add, push, reset, synchronize, finish. So urgent, we already know. If this bit is set, then the destination knows that this is urgent. Oh, actually this means that this is urgent, and that the urgent pointer field is significant. So there is an urgent pointer here. This is the whole thing is a pointer, but this can be ignored. It will be ignored if this bit is not set. When this bit is set, then there is real urgent stuff, and this pointer will tell you what is urgent. Alright, urgent pointer. Add field is significant. If this bit is set, then the add field is significant. Push function. So this packet is pushed. Reset connection. So when there is a problem, the source may say, sorry, I think our sequence numbers are all messed up. And so let's reset the connection, and here's my new, let's start a new connection. Synchronize sequence number. Syn means start, and fin means finish. Yeah. 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 Okay, maybe your partner can tell you the next. Now let me explain again one more time, because some of you didn't hear before. Does anybody else here know as to why the sequence number doesn't start at 1? Anybody on this side? Nobody knows? Yeah, go ahead. Yeah, so the problem is that could be old packets that could be floating around with the old numbers, so we don't use that number as long as possible. So once we use some numbers, we don't use them again for a long time. So we just keep going up and up and up and up. Our sequence number keeps going up and up and up, and then we go back to 0. Yeah, so maybe you can probably start for the source port again, but basically you don't reuse as much as possible. So they don't have to start from 0. You could start from 0 again, but basically if there's an old message for the same IP address, for the same destination address, for the same port number, it could be confusing. No. There is no such thing as first connection. What connection is the first connection? I booted the computer? No. So we don't know. I could have done it in my previous life. So I sent something, the computer went down, crashed, rebooted it. Now I'm connecting the computer again. Is that the first connection?
So by saying an old connection, you mean an old...
It could be any old. It could be 2 months old. It could be either possibility. It could be any possibility. I'm just saying. I'm just making up these examples. But it could be that the packet was. You think that this is your first connection, but there is no such thing as a first connection. Computers can reboot, right? And they think this is first connection, but they had the same connection before they crashed. So there is no such thing as first connection. And so basically, every connection you start with whatever number you want to get. You could start with 0. It's not a bad number, except that you don't want to reuse that very soon. Okay. No, it doesn't know that. It doesn't know that. It just starts from some high number. You just start and we are taking a chance. So if you crashed and then you start again, you could start from 0. You could start from 2,000. You could start from 20,000. All numbers are equally good. Except, So, but the thing is, if there was any way that you do the number, then you start from whatever number. So the number doesn't matter. Basically, the key idea is that the SYN bit present, you could use any number to start the connection. So your question is valid that if you crash, you really as well start from 0 because who knows, you might have wrapped around to 0. So you're taking a chance. Yeah. Any other question left? Okay. All right. So where are we? Checksum. Checksum covers the segment plus a pseudo header, and this is important, and I will go into this later on. Is that it is not just the header that I showed you, it is more than that header. So something called a pseudo header is added, and that includes all the fields from IP, source address, destination address, protocol, segment length, and so on and so forth. So IP packet as well, and then you calculate the checksum. Okay. Urgent pointer points to the, and by the way, checksum is that same formula we use. One's complement of the one's complement sum of all the bytes. That is TCP checksum. Anybody remember the one's complement of the one's complement sum? Right. So that is TCP checksum. Urgent pointer. Urgent pointer points to the byte following the urgent data. Let the receiver know how much data it should deliver right away. So, here is the data, and maybe up to here it is urgent. So it says that up to byte number 1300 it is urgent, and so this 1300 goes there. Yeah. This one says, yeah. So basically, if it is urgent, you won't put it at the end here. First of all, because if it is urgent, really you don't want to send anyway. It doesn't matter. You are not really going to send out of orders. This will have to be delivered before urgent will go. So you really need to know where the urgent ends. After that, it may not be urgent at all. So you just point to the end of the urgent data. All right, options. Now there are many options which exist and which have been added later on. So one is MSS, maximum segment size. Does not include the TCP header. The default MSS is 536 bytes. So this data size is called MSS, maximum segment size. Not this header is not included. So this cannot be more than 5, whatever number you select.
Select this number?
Or you select the number. Basically, on your computer, you select the number.
So the client will next select the number?
Yeah.
So we can't override it?
No. No, you cannot override it because there's a reason why the client selected that number, and that reason could be that it doesn't have only that much memory it has, it cannot hold any more in the memory, or it could be that there is a router on the way which cannot hold any more in the memory, somehow it figured that out. Yeah, so server has the same right as client has the same right. They could each select their own MSS. Now, I see what you're coming to now. You're coming is that if the server says I want to use 2,000, maybe 2 million my MSS, then the client says, wait a minute, I have only 536 bytes of memory. So it is actually then rejected. The connection will be rejected. So it will put MSS of whatever number, the other side can reject that.
There is no negotiation.
That's a negotiation. That's exactly, rejecting a request is a negotiation. Does it make sense? So suppose you send me 2,000 as a required MSS, I say reject. I don't send you any acknowledgement for that, basically. So there's a negotiation. Window scale factor. So initially when this was designed, we had windows of 4, 5, 6, 7, 8, and now we have window of 8,000. There's not enough space in the window field to put that number. So what we do is we have a scale factor, and we multiply the power of 2 with that window. So the number, this window which used to be in bytes, now it could be in kilobytes, megabytes, whatever you need the unit to be, because there's a multiplier. Selective ACK permitted. So that's another option, is that please give me a bitmap of the packets received. So you don't have to, so you can just say I received 16, I received 17, I didn't receive 18, then I received 19. So actually it's not by packet numbers, it is again by byte numbers. So you say, well, I received from 1 through 10, then I did receive from 11 to 22, but I received 23 to 45. So you can just send this whole map of what you received. Selective ACK. Timestamp. That please timestamp the packets so that I can measure somehow what the delay is. No op means nothing, it is just a filler. End of options, basically no more options. So the options are basically always, so they have a kind 0, type 0, length is 1, end of valid options. Kind 1 is length is 1 is no op. Kind 2 is length is 4 is maximum segment size. The option 3 is window scale factor, the length is 3 bytes. And type 8 is timestamp 10 bytes. Alright, end of options. Stop looking for further options. No op means ignore this, and MSS does not include the TCP address. So remember that part. Maximum segment size. This is another confusion. Every time you see the field called length in any packet in any IP protocols, we have to figure out that length indicates what. Size indicates what. So in the case of TCP, segment size, normal brain would say this whole thing is a segment, right? But they mean that the segment size is just the data field. Checksum. And this is another crazy thing. Well, actually, at that time it was not crazy, but now it feels crazy. Is that when you calculate the checksum for TCP, you add the IP header first in TCP. Yeah. Yeah. Yeah, okay, that's a good question. So the options are written as what we call TLV. What is TLV? Tender, TLC, tender, loving care. But TLV is type, length, and value. So the first byte is type, the second byte is length, and the rest of the bytes are value. Yeah. That's why 1 byte, 256 types should be good enough. So the first byte is the type, then the second byte is the length, and then you have whatever length is, that many bytes of. No, so then you will end of option. So you will put 0, 1. No, because the length 0 would not make sense. See, the thing is, by the time you put, yeah. You see, this is what I think why it is not 0, is that this length, now I have to verify this though, actually I have to verify this by going into detail. This length includes probably this length field itself. So no op is 1 byte. So there is nothing after this, basically. This is 1 byte, which is the length itself. And similarly, the end of option is 1 byte, which is the length itself. This is all arbitrary decision, you know. The thing is, in those days, 1974, somebody sat down, one person, which his name was Bincer, by the way, you all know. So Bincer sat down and wrote a protocol, whatever he thought was right? And so now people will question it much more. So now it looks like if you follow the same logic, then you will be left with 3 bytes and Windows scale factor for 2 bytes. I have to verify this though. That's why I'm saying I'm not sure what this length field is, because you asked the question why this 1 here. I was thinking that no output says 0. Yeah, but I have to verify that. Alright, we are coming to the end, so let me see how far we can go. Oh, I want to just finish this slide if I can, is that checksum. So before you do the checksum, you put a header of IP header here. So you put the IP header will contain source address, destination address, zeros, protocol type, and TCP length. You put this pseudo header, means it doesn't really exist because this is TCP, right? But you put that header and then you do the checksum. And then you give it to IP. IP will put the real header. When you receive it back, IP will remove its header and give it to you back, this part, your TCP packet, and you put this pseudo header back again and calculate the checksum. Okay? So this is a clear layer violation because TCP cannot run on any protocol other than IP because this header does not belong to any other protocol. Okay? So this is the end for today. This is the end for the exam 1. We will actually, okay, anyway, we can ask anything up to this slide, 35. We will not ask anything about this slide, 36.